Hello again. Tonight we're going to talk about Casimir density dark energy expansion, or my postulation on the dark energy expansion and why I found out why it's dark, and also maybe not the source that most people think of. So I'm apt for connecting dots where other people typically don't see the dots, and also known for postulations that once I get done with them, I go, well, obviously I can't prove it. I don't have a funding or a research team or expensive facilities. I can't submit. I don't have a PhD. I can't submit to peer-reviewed journals and such. So it's up to somebody else to just see what I say, and if it seems to have legs, as the saying goes, somebody else go do with it. I don't even have to say. And remember where you heard it here first. Just I would like to advance the species and the concept. So the one that the best is stellar mass black holes are merely top quark stars, because we know about neutron stars and strange stars and the next thing up kind of thing. But in science, as opposed to mathematics, postulations are less grounded than theories. They don't have peer review, maybe, don't have confirmation of observations and such, but they're kind of where the circle of scientific method starts. Is somebody goes, from what I see, I think it, is the source of this, the cause of this, maybe this, the starting point. And then you've got to go do analysis and observations and such. And then you come back around. If they're confirmed, then you might have a theory. If they're not confirmed, reset back to the front and start over again. In mathematics, postulations are different. Postulations are undenied statements of accepted fact, and they're generally not something you expect a theory to prove them, such as point, line, and plane in geometry. They're the basis of things, the precepts, if you were, that you just have to kind of accept. So there's a difference between scientific method postulations and then mathematic precepts or postulations. But now that we can do all sorts of fabrications, with particles as well as materials, and we can make things at the quantum scale, we're starting to find out that the bigger stuff that we used to have in order to make a particular physics effect work, we can do them at a quantum scale or a nanoscale that aren't necessarily the thing you're used to. So, for example, if you have a flat material and you drill nanoscale holes through it of different sizes, then only certain colors, wavelengths will fit through those holes, and you can effectively create a prism without that typical triangular wedge shape of glass, and have an actually more efficient prism, because it absolutely will not let larger wavelengths through smaller holes. So they have things like quantum scale Fresnel super lenses. These are nanoscale lenses where the steps, the little circular parts of the lens, are nanometers. And you can create a lens that is incredibly small, but still incredibly accurate, and can magnify many times with a very small lens. We have inertial sensors that, know when the airplane, the spacecraft, the rocket is turning or whatever, it's, nosing down, or we have nanoscale electrical devices, sensors that can sense that movement in G forces and read it out digitally. So a lot of the things that we maybe never have thought possible, but now that we can do things at the quantum level, we're starting to find out that they are possible. And if you don't have it by now, you'll have quantum dot video displays for your TV. These are little tiny organic plastic dots that the diameter of the plastic dot is matched to the wavelength of the color of light you want. So you have red, green, and blue, and there's no difference in the materials. There's a difference in the diameter of the individual particles and how many of them you have in a little circular thing, like a corral that holds the particles in there. So, and there's my favorite, which is the Nobel Prize in Physics for photonic tweezers. This is where very low intensity lasers are used as they bounce off of virus and bacteria to move them around on your electron microscope. So you don't have to get in there with mechanical things. You can move stuff to a very fine degree just with the transfer of momentum from light. The more we know about quantum, the more things we can do with it. I'm going to go over this one rather quickly, but this is sort of my take on quark stars being top quark stars, and that's how you get a stellar mass black hole. It's a prior postulation. It's just a progression. And when you think about the various end stage lives of stars, and you see, well, we got a white dwarf, and then we got a neutron star, and you keep progressing, and you have other types of neutron stars where the neutrons get shredded down due to gravity, and now it's just quarks up and down, and then the more refinement from there, further progression is, well, maybe you've got strange quarks and strange matter stars, but then there's this gap, and the next step from there is not another kind of quark star, it's a black hole. And the difference between a strange quark and a top quark is a lot of energy. And I represent that's that gap. When you see that gap between strange stars and then black holes, the distance of that energy level is about similar to the progressive step from strange quark to top quark. So stellar mass black holes are nothing more than top quark matter stars. I did a whole presentation on that, but we won't get into that in this particular presentation. So my latest postulation, aka brain fart, is that I think I've connected some dots and found out why we have dark energy expanding the universe, making it expand outward. It starts with a little thing called the Casimir effect that is typically recognized for attraction and not repulsion, and we'll get to that. We also know this thing about progression of redshifting of photons. So the universe expands, stretches, photons start getting redder and redder, and eventually go from higher energy to visible light to red to infrared to radio waves, and it's a progression. And at some point, they're no longer visible, they're dark. And if you continue this progression, eventually you'll get to photons that no longer interact with and excite atoms and make photons. They just become dark, undetectable. And we'll get into the details of that. And then the Casimir effect, when you separate the plates, and we'll describe the Casimir effect shortly, when you separate the plates by closer and closer and closer distances, at about 50 billionths of a meter, 50 nanometers, the attraction, in other words, the outside force of the plates inward, suddenly becomes a repulsion to push the plates outward. But you've got to get down to 50 nanometers or less. And that's where the whole thing comes together, is if you can make photons that are longer and longer and longer wavelengths, lower and lower and lower energy, then eventually you'll get to this threshold where if you pack enough of them together so that they're closer than 50 nanometers, you now have a repulsion effect rather than an attraction. And on a cosmic scale, this could be a possible explanation for the expansion of the universe. And as more and more photons shift downwards and get longer and longer wavelengths, you have an increasing expansion rate. And we actually see that. As the Hubble constant's not a constant, it's an acceleration that increases over time. So here's the Casimir effect. Originally, they started out, this is back from the late 1930s, early 1940s, they found that if you take two metallic plates, two conductors, and you push them closer and closer and closer and closer together at a point of microns, millionths of a meter, you'll notice that the plates want to go together. They want to collapse together. And it's not because you increased any forces on the outside. All you did was reduce the separation on the inside. And they first thought, well, that's because you've got a vacuum between the plates, because air won't fit in there anymore. So there's a vacuum. And what they found out was, no, it's more like subatomic particles, particularly photons and electrons. When their energy level, their wavelength, gets to be larger on the outside and smaller on the inside, then only the things with the smaller wavelength will exist on the inside. And then on the outside of the plates, things with larger and smaller wavelengths will exist. And therefore, you get this differential force that wants to push the plates together. Of the last few years, we've pushed that even farther and said, what if we squeeze the plates together really, really, really close? And we said, do we really need a vacuum in there? And we started playing, I mean, scientific efforts, research efforts, started playing with the Casimir effect and saying, what if we squeeze it really close together? Do we need a vacuum? Do the plates need to be metallic? And we found out some things. And we found out that if you push the plates closer together than 50 billionths of a meter, 50 nanometers, that instead of an outside squeezing force pushing the plates together, you actually get a repulsion force pushing the plates apart. They don't quite know why. My thought is it's quantum tunneling. The stuff on the inside jumps through the plates and goes on the outside. The other thing that they learned is the plates don't have to actually be metallic, but they do need to be highly reflective. So they don't need to be conductive, but they need to be reflective, which says the effect here is predominantly not electrons, which are electromagnetically conductive. They're photons, which would transfer momentum to the plates because they're reflective. So switching that from Casimir effect being close enough together that it's now rooted in radiation reflection pressure of the remaining photons on the inside. And they said, well, do we really need a vacuum? And they changed the vacuum to a very uniform density material. And they found out, nope, the effect still exists if you put a very small amount of uniform material, that the same Casimir effect exists. So yeah, we learned that if you get it close enough together, the outside compression now becomes a repulsion. And we all know about photons shifting their wavelength from shorter wavelengths to longer wavelengths, redshift as they call it. As the universe grows, we notice that as more and more things get redshifted, they go from higher energy to lower energy, and they go from like gamma to X to UV to visible to red to infrared to microwave to longer and longer radio wavelengths. And there doesn't seem to be a bottom on that. So as things shift further and further down, the energy levels get lower, the wavelength gets much longer. So there's a progression there that has no current known bottom. So if a photon interacts and essentially changes the quantum level of an electron in an atom, and then you get a photon out and the electron falls back down to its ground state, at what point is there just not enough energy left in the photons? And there's a chart. Look at that. So the vertical lines indicate different elements, and then the horizontal rows are the essentially the levels of the electrons within the atoms, and then the numbers down along the bottom represent the essentially the electron volt levels. So you can see that much like people would say, what's a very reactive material? Lithium is. Okay, that's good. That's good. What's another very reactive material? Well, cesium. Okay, so I've got a little red box there, cesium. But people will say, what atom is the one that can react best to the lowest possible energy? And as it turns out, it's not hydrogen, which is what people expect it to be. It's actually cesium, and it's by a significant difference in electron volts. So just think of it as if you have a photon that has less than 3.89 electron volts of energy associated with its wavelength and its frequency, if it's less than that, it won't even interact with cesium or any other element in the periodic table. So if a photon has less energy than that, then you can't directly do the photoelectric effect and produce electrons and therefore measure that energy level. So we can't directly detect them, and therefore those photons of low energy should be essentially undetectable, aka dark. Well, we found out that as things get lower and lower, we can actually use other than the photoelectric effect to measure those extremely low energy levels. And it's a combination of something called resonance, and we use antennas for that because we're not talking about high energies of light. We're talking about the bottom end of the radio spectrum, and we use antennas that are metallic to resonate and therefore build up more energy, and now we can detect them. And then we use a low noise amplifier to actually pull the signal out of the noise. So there's a couple of bands of radio energy, and my amateur radio astronomer enthusiasts in this will like this part. There's super low frequency, which is 30 to 300 hertz. And that's a very long wavelength. It can be over 10,000 kilometers or 6,210 miles, a single photon wavelength. And this sort of stuff penetrates. Wavelengths of that long can penetrate meters of seawater. So it made it useful for communicating with deep ocean submarines. And the US actually had a program called Seafarer. And the follow-up to that was something associated with something called TACAMO that is used for communicating nuclear response to US submarines. They've since found better ways than SLF to do this, but Russia still has a program and it operates at 83 hertz, not megahertz, not gigahertz, not kilohertz, hertz. That's cycles per second. The data rates are so low in bits per second, you can't do live voice transmissions. You have to just use data. So it might take minutes for a single message over TACAMO or the Russian equivalent to be received. And you can't transmit a response back because these are super long wavelengths. So if you're transmitting, the antenna needs to be incredibly long. And the power you have to put in the antenna to make it oscillate at this very low frequency is enormous. So each country like US and Russia gets one transmitter. And then you can have very small receivers because these frequencies don't have a lot of interference on them because they're very unique. Nothing else transmits them. And you boost the signal, and then you use your analog to digital converter, and now you can read out the signal. And for most people that aren't aware of it, hey, what about the energy level of cameras? CCDs and CMOS cameras use something called photodiode or SIPM, SI standing for silicon phosphorus manganese, I think it's manganese, amplification. So even cameras are well below these frequency ranges, and so they have to use something that will boost the signal, and then it goes through the analog digital converter to create your pixels for your image. But physics doesn't stop at SLF. The progression keeps going. But there are man-made forms of super low frequency. Here's one that comes to mind as soon as I point it out. The power grid. Well, yeah, there's a whole bunch of 50 hertz and 60 hertz stuff that's all over the place. Yes, and I, with a software-defined radio receiver, have actually just used a transformer coil in free space to pick up 60 hertz from the Florida Power & Light power grid. If you have multiple generators in an area, like, FP&L, 2 different power generating plants in Florida, you may actually get sometimes the grid from one, sometimes the grid from the other, and they're not perfectly synchronized to one another. So your 60 hertz can be a little more than 60, a little less than 60. And there's actually radio frequency reflections occurring in all this metallic stuff you use for the power grid and transformers and such. So you might find that it's some amount at 60 hertz, and there's others at 30 hertz, and there's others at 120 hertz. They're fractional and multiple harmonics of the original frequency, but they're easy to identify. And then the next band down is called extremely low frequency radio. I know they have these weird scaling names. It's like ultra and super and low and extremely low and super low. And what do you call the one after that? You're going to love it. So ELF is 3 to 30 hertz. This is kind of like the lowest internationally recognized radio band. It's 3 hertz to 30 hertz, not kilohertz, not megahertz, just hertz. And if you want to know what the energy level of 3 hertz is, it's 12.4. Remember me talking about electron volts? This is femto electron volts. Now, nano, or a billionth, is times 10 to the minus 9. Pico is minus 12. Femto is minus 15. So this is 3 orders of magnitude less energy than a nano electron volt. The wavelength is almost 100,000 kilometers or 62,000 miles. That's a single photon with a wavelength that long. So if you want to transmit in ELF, you need a really big antenna and a lot of power. But if you're receiving it, like, would be on a submarine, all you need is a simple coil of wire because there's not much radio frequency interference at that band. But because you need it amplified like crazy, you need a better antenna, you need a lower noise amplifier, an LNA that's even better to be able to get signal out of it. But that's ELF. There's nothing that says the physics stops there. The physics says like an abrupt stop at 3 hertz. No, that would just be not making sense. But there are natural sources of ELF. Speaking of lightning, we were talking about lightning earlier. Lightning strikes interacting with the Earth's magnetic field generates radio pulses in the 3 to 30 hertz range. Remember, you're talking about if you want to transmit at that low a frequency, you better have a lot of power. Lightning has a lot of power, and the Earth's electromagnetic field is a good inductor. So lightning striking the Earth creates very low frequencies. But there's this other thing that those familiar with the ionosphere and doing ham radio stuff, what you don't realize is there's a specific frequency that the Earth's surface as a conductor resonates with the ionosphere itself. And that's called Schumann resonance. And it's at about 8 hertz. It has a wavelength of 37,000 kilometers or 23,000 miles. That's larger than the diameter of the Earth. So very, very long, very low energy. But the one that I found amazing was brainwaves. Alpha brainwaves are 8 to 12 hertz. I had to look that up. I said, are you sure you don't mean kilohertz? No, it's hertz. Well, how can a brain operating inside something as small as a skull generate radio wavelengths at 8 to 12 hertz when, if we're going to do that with electronics, we need massive power and very large antennas? Well, it turns out that these are side effect transmissions of neurochemistry. And they don't have to transmit very far because it's just neuron to neuron electrical discharges creating these low frequency wavelengths, and they only have to go from one neuron to another. So they're traveling, microns, and they're easy to pick up outside the brain because there's nothing else transmitting inside your skull at those frequencies. So you can see the various alpha and beta bands of brain activity. I just thought that would be like electronics, man-made stuff has to have big, powerful, but nature finds a way to do it. It's just a side effect. Okay, remember me saying they have silly acronyms for these things? Here's the one that internationally they find too silly. TLF, or tremendously low frequency radio. They ran out of superlatives. Oh, well, we got down to extremely. What's after extremely? Hyperbolic? No, tremendously. So for radio frequencies that are below 3 hertz down into the fractions of hertz, they're called tremendously low frequency radio. And the ITU has yet to recognize TLF as a band. Well, why would that be? Well, we don't have any transmitters and we haven't created any receivers that can actually do this. And therefore, maybe it's just theoretical. If it's just theoretical, why wouldn't it exist? Because we found that the progression takes us all the way from gamma rays, UV, visible, red, infrared, microwaves, and all these different bands of radio frequencies right out the bottom. And there's nothing stopping it. There's no ceiling on it. As long as the energy level per photon is greater than 0, even if it's infinitesimally small, it's still a photon. But since its energy level is so low, it will not energize an electron to produce a photon. Therefore, we have no technology for directly detecting it. So 1 hertz, not sub 1 hertz, but just 1 hertz itself as an even smaller number, 4.136 times 10 to the minus 15th. We're in the femto, so it went from 14 to 15. And the wavelength, here's the fascinating thing. 1 hertz, 1 cycle per second, is the speed of light. 299,792.5 kilometers, or 186,300 miles. So 1 hertz has a direct relationship with the speed of light. Fascinating. For reference purposes, the Earth-Moon average distance is 382,000 kilometers or 238,000 miles. And we're talking about something that's a little longer than that. Oh, sorry, a little less than that. And the old comment about if you want to transmit a radio signal to the moon, it takes a little over 1 second. Well, that's how you get those numbers. So if we wanted to transmit at 1 hertz, we'd need a really long antenna. And the more that we make it a fractional length of the wavelength, the more power we need to put into it. So we're not about to create a TLF transmitter anytime soon. What if we wanted to receive? Well, now we need a bigger receiving antenna, a higher output, more sensitive receiving system. And we don't have those anymore because we've run out of the excitation energy of any of the elements. We have, much like they found out that when you get below light and you have metallic antennas and you have resonating electromagnetic frequencies you can receive on radio, we need to come up with something akin to that where we can receive to even smaller fractions of a hertz. Just think of it as physics doesn't prevent the existence of it, and we see the progression where there's no bottom to it, and we see that the number is still greater than 0. So those photons still exist, but we have no technology to detect them. And they'll pass through pretty much any material because they don't interact with the atoms. So they would be photons that are dark, much like neutrinos. At one time, there was this thing called WIMPs, weakly interacting particles. I would say that these very low frequency, extremely long wavelength, low energy photons that don't interact with anything, they're pretty WIMP-like, but just connecting the dots. So now we have the Casimir effect. We have photons that are getting longer and longer and lower energy, and there's nothing that makes them go away. So we're going to have an accumulation of them. And therefore, once the quantity of non-excitation photons, whose energy level is below the lowest excitation level and below current antenna and amplifier technology, and the packing density gets to be 50 nanometers or less, if that density is smaller and smaller, then we'll get a repulsive force or expansion from the Casimir effect, which would exist and continue to accumulate throughout the universe. And therefore, from the early universe to the later universe, more and more of them are accumulating. So greater the expansion force, or I've just given a nice buzzwordy label, Casimir density dark energy expansion. This is my take on why the universe is expanding and why we can't see what's causing it to expand. And it's just photons. So they still look for dark energy, and there's actually something called the Dark Energy Spectroscopic Instrument, and it's on the Mayall telescope in Kitt Peak, Arizona. And this instrument is supposed to be able to detect dark energy. They postulated that dark energy is the source for expansion of the universe. If you didn't know the prior postulation that I came up with, then this would obviously make sense. But the way that they're saying this is this source of energy is making black holes bigger, and they have no detection of what this material is that's supposedly making black holes bigger. And if a black hole is getting bigger, shouldn't its mass be increased to the point where eventually they'll become supermassive black holes because they're feeding on all the stuff that's around them? If they are feeding and they're becoming more massive, then anything that's orbiting it, like very high-speed orbiting stars near a black hole, shouldn't they be changing their orbits if the black hole's getting bigger over time? And although the DESI is detecting so-called dark energy, they're not detecting the other effects. And if they're not detectable, then they're just attributing it to dark energy. But it's kind of like your conclusion should have evidence for it, but the absence of the evidence is how you're getting to your conclusion. So it's like, okay, I hear what you're saying, but skeptic. So once again, we've come to the burden of proof not being mine. I don't have the funding, the staffing, the observatories to develop whatever new technology we need to measure the tremendously low frequency radio signals. Let's hope it's not the same thing when they found the cosmic microwave background and they thought it was just bird poop on the inside of their antenna. But a little chart here kind of gives you the relationship: frequency, wavelength, the amount of energy per photon, and whether we've detected it or not. So 3 hertz. Yeah, we've detected 3 hertz. 1 hertz. We have yet to have the technology to detect 1 hertz. And there's this thing called the Planck limit. If the wavelength of the photon just keeps getting longer and longer and longer, eventually it will reach the Planck, not the Planck subatomic limit, but the Planck superscalar limit. And that would be about 1,883,693 kilometers. So I would think that if the Planck limit is a limit, then that would be it. But you'll also notice the energy level of the Planck limit, the Planck length maximum limit, is a very small number. But we're already at 4 times 10 to the minus 15th, and we can't detect it. So if we actually got to the Planck limit in electron volts, how would we ever detect it? So it's a theoretical maximum. But maybe that's the bottom. Don't know. We have to have instruments to detect these things, measure them, have peer reviews and confirmations and posts in journals and stuff that's not things I can do easily. But if you want to be able to detect something dark, you can not directly detect it, you can indirectly detect it. Instead of using a black hole, which is already already very massive, let's use its precursor. Let's use a neutron star. If you have a neutron star that starts and it's a neutron star, it's created a lot of outgassing and pushed a lot of stuff away. Millions of years later, after it's pushed most of the stuff away and there's nothing nearby for it to consume, you'll have some things that are orbiting at large distances around this neutron star. If there was stuff falling into the neutron star that was increasing its mass, then you should be able to see changes over maybe decades in the orbits of these very closely orbiting stars. They would accelerate, their orbital parameters would become different, but you won't see this on stars orbiting black holes because the black hole's gravity is already so large and they've been orbiting it for so long that there's no instability there. But if you start with a fairly new, in galactic speaking, neutron star that's already pushed all the debris out and has a small sampling of stars rotating around it, you measure differences in their orbital characteristics. If you can measure any difference at all, it must mean that something's coming into the neutron star that is altering its mass, therefore altering the orbits of things around it. And if you didn't see it going in, it's undetectable. That doesn't mean it doesn't exist. That just means you can't see it. But then as I thought about it, I said, which came first, chickens or eggs? If black holes are supposed to be consuming this stuff, if neutron stars are supposed to be consuming this stuff, then they're going to be the mitigators. They're going to be the stability things that prevent more and more of these very long wavelength photons from building up in the universe. They're basically picking up the garbage waste of photons that longer and longer wavelengths, lengthening wavelengths, would create. So as more photons get longer wavelengths, things like neutron stars and black holes suck them in and compress them away. But which came first? The expansion of the universe, which created the longer and longer wavelength photons, or the longer and longer photons that the black holes and the quasars created the gravity to cause the effect, or as I refer to it in the end there, George, and this is actually a quote from a speech by JFK, George Bernard Shaw once wrote, "Some people see things as they are and say, why? I dream of things that never were and say, why not?" So I look at it as, if there's a progression in physics, why do you arbitrarily put a top or a bottom on that progression when you have no evidence of that cap, either too big or too small? So the progression continues. We just can't detect it. So in summary, a postulation is a starting point for the scientific method. Postulations are easy, don't require proof, peer review, or observations. It also means that postulations can often be proven incorrect as soon as you start getting evidence. Proven effects are one aspect of science that can tie things to others. And no better example than the Nobel Prize for optical tweezers, pointing out that radiation reflection pressure transfers momentum and has an effect. So when photons are sufficiently tightly enclosed, less than 50 nanometers apart, you get an expansion effect, not an attraction effect. And we know that photon frequencies less than 12.4 femtoelectron volts don't interact with any of the material, any of the elements in the table of elements. Nothing stops them from existing. We can, with radio antennas that are metallic, resonate the wavelengths and pick up things, and then use low noise amplifiers to pick up radio signals that are fairly low energy. But we also know that this red shifting and non-interacting photons will just continue out the bottom. We don't see a lower limit on it. So at some point, they're below our technology to detect them. So they are dark or undetectable, at least not directly. Maybe someday we can come up with some technology to indirectly detect them, much like we've done for neutrinos, but right now they're dark and undetectable. And I think that as the wavelengths of the photons get to be longer and longer, and we can't detect them anymore, that doesn't mean they die out. And at sufficient densities, it might induce a collective repulsion, or what they refer to as dark energy expanding the universe. Or as I pointed out, the postulation is Casimir density dark energy expansion. And I went through all the underlying scientific principles and have links for all that stuff, especially the one on chirality turns the Casimir force instead of attractive, repulsive. The greatest redshift that we've detected, and we had to use the James Webb Space Telescope. What is an electron volt? Is that like a regular volt? No, electron volt is a very small amount of energy, well, fractionally below what a volt is. And then from the National Institutes of Health, what the minimum excitation energy for elements in periodic table of elements is. And for those not familiar with what is this electromagnetic spectrum of which you speak, and what's the minimum detectable signal? Antennas, how antennas work, radio frequencies, and for those that aren't familiar with the the nanos and picos and femtos, you can go read about those. Planck constants. There's all sorts of Planck constants for lengths, big lengths, small lengths, time, masses. There's all sorts of upper and lower limits on things. And then what is this LNA of which I speak, low noise amplifiers? And for people that are familiar with the more analog version of an LNA, it's called a photomultiplier tube. And then the silicon equivalent of that, used in most digital cameras. And then the indirect effect of SIPM photomultipliers, something called an avalanche photodiode. And then the bands ELF and SLF. And then the detections by DESI. And then the reference to dark energy coming from black holes. Okay, I know beyond a lot, and it'll probably play well once the public gets their eyes and ears on it. But it took me a while to put all this stuff together and to finally find my round to it so I could put it all together and get it out. Comments? Questions?
Very nice.
It's a lot of stuff to absorb.
Yeah. As we as a species create better and better instruments for observing things that our physiologic sensors have no capability of detecting and observing, we find that the universe is a lot more complicated. Things are happening in split seconds that are very very detailed, and we just never see any of that because we can't see the individual steps along the path. And the more that we observe, the more we find that things that are progressive, either upwards or downwards, don't really have easy to come by limits. So until you find a limit, don't impose a limit. We may eventually find technology that says that maybe the Planck limits aren't limits, but as far as our current understanding of physics, the Planck limits are limits. We have yet to reach them. So until we like bump our head against it, we do that with integrated circuits. There's the concept that we kept shrinking the features of the transistors of integrated circuits smaller and smaller and smaller and smaller. And we moved out of white light to closer to ultraviolet light. And now we're into deep ultraviolet light to get the wavelength down short enough where we can, through photolithography, make smaller and smaller transistors. And we got to about 8 nanometers. And we found out that the electrons don't behave well at that level. Instead of like the vertical fence being the gate for the transistor, you put an electron on one side and it just goes right through the gate at a random probability. And this is called tunneling, quantum tunneling. And when you make things too small, physics kind of falls apart. So 8 nanometers is the finest feature resolution we can do for transistors. So they pulled it back up to, I think it's around 13 nanometers. And they found the probability of tunneling drops off. And so now they can make that be the ultimate Moore's limit of how small they can make a single transistor. And they said, why are we making transistors in 2 dimensions? If you remember the old Star Trek adage, Spock and Kirk talking about, 3-dimensional thinking. So now they're building transistors vertically. So instead of having a single transistor be planar, you have stacks of transistors. And I think they're up to around 20 some odd vertically stacked transistors. And that's how you get to, how do we get to 1 billion transistors on a chip like, the size of a cracker? It's because we stopped being just 2 dimensions and we went 3 dimensions. And now we're going super scalar and we're actually making an integrated circuit that's the size of a dinner napkin. But inside that integrated circuit, there's a whole bunch of these super scalar parts that are all essentially built together as one giant integrated circuit. So that's how you get to many billions of transistors in next generation computers. And why, like I was seeing where the latest AMD computer chip has like 192 processing cores on it. I can remember when we had duo core. Hey, I've got 2 cores, and people would go, I've got 4 cores. And then, now mobile phones have 6 and 8 cores. It's just like, well, that's just this year's generation. And then you've got server computer chips that do the supercomputer processing, 192 cores per processing chip, but the chip is like the size of a dinner napkin.
Yeah, the problem is how to address them.
Yes, it's like, how do you give them that much work to do? And if you give them work to do, how do you communicate the data that they're going to need to do the work? And when they come away with the result, how do you keep the data back from them? So like they're putting more and more memory directly associated with the processors, with the cores. And one of the things that they found out, if you remember, there's this concept called hyper threading, where when you went to do a series of instructions, you would hit a point where, I got to do a memory fetch now. Well, that's going to take a long time compared to the processing speed of the processor. So you would branch off and you would create a hyper thread that would continue using whatever data it didn't need for memory, like in registers. It would continue using the register data that you previously loaded to do more of the instructions up until it hit the stop again and said, well, I'm done. So you would have hyper threading. There would be like each core would get a hyper thread. And then they got to up to 4 hyper threads. And they said, any more hyper threads, and we're just kind of like, we can't use them all the time. So it's a waste of the silicon. Power consumption. So now what they're saying is, don't need no stinking hyper threading. When you got 192 cores, just use all the cores. And they've got cache, primary cache, secondary cache, tertiary cache, and all of these caches are getting slower and slower and slower memory to get all the way up to the main memory that's processing stuff in like 15 nanoseconds. So inside the processing chip, the processor is cycling at the femtosecond level. And then when you get to the caches, we're down at the picosecond level. And then when you get to the main memory now, it's like, it's a small number of nanoseconds. And a nanosecond is a billionth of a second. So every time we think we're going to bump our heads on some progression, we just find a way to get around it.
Yeah.
So, why should it be anything different with radios and lower frequencies, longer and longer wavelengths? Just keep cooking up new technology where, like, I see the roadblock, we'll go around that.
Or a breakthrough comes in, something we didn't even think of.
Yeah. Well, I mean, we thought there was a cosmic microwave background, and until we created the instruments for measuring different amplitude and wavelength kinds of gravity waves, we didn't know there's a potential for a gravity wave background as well, because we never had any sensors that were capable of detecting it until we did. And now that we do, let's improve those and see if there's a ubiquitous gravity wave background. But until we create the sensing network, we don't know. So how many people are going to need an analgesic? Need some aspirin, some Tylenol? That's just too much. My head hurt. Okay.
Yeah, it really is.
I understand that. Why do you think it took me several weeks to put this together?
Oh, yes.
I would go up to a certain point and go, that's going to take me a while to understand that.
Mm.
So how do you get your postulation in front of some professional astrophysicists for consideration?
I got this thing called a YouTube channel, and I can take the video, edit it, and post it to the general public. And
but that's there's so much noise out there on YouTube. So how do you get somebody to a professional to look at it?
I know, but there are people that follow me that are serious science people because they enjoy entertainment. I love the ones when I got, no, that's not the way it works. That's not possible. And then I'll give them a link to a couple of papers that are peer reviewed going, well, that may have been the case, but that's no longer the case. And then they go away quietly. I had a lot of fun with the one on the existence of top quark stars, even if they're not black holes. They can't exist because top quarks, they can't be created in any numbers, and they don't last long. And then research that's been peer reviewed from 2 different sources, and in 2022 and 2023, I sent them links on, now we're creating top quarks in quantity, and they're lasting for a little more than 1 second. So the same things that we held true for strange quarks, creating them in small quantities and then lasting a little more than 1 second, which was the evidence for why we can have strange quark stars. This is also the evidence as to why we can have top quark stars. And then they go away and I never hear from them again. So yes, I think there are people watching, which is why I enjoy exchanging emails with certain people at NASA. You remember back when I was trying to do measurements of basically transfer of momentum by photons, and this is before the Nobel Prize in optical tweezers came out, and I was trying to find a place that would measure nanonewtons of force. And I couldn't find any place. I could obviously buy no instruments that would measure that. There were no universities in my area that could measure that. And I happened to be at a medical device face-to-face meeting in Cleveland, Ohio. And I went to the museum that's there, the Science Museum. And they had an exhibition there from the Glenn Research Institute, a NASA facility. And they showed all the things that the Glenn Research was doing. And one of the things was for ion propulsion and newer lower energy propulsion, the Glenn Research Center actually had a nanonewton scale where they could measure the force produced by these very small propulsion force, ion propulsion engines, Hall effect engines. And so I got contact there and said, basically, what would it take for me to use the facilities? Like, no, you got to have a principal scientist that's a PhD in the area. And okay, sorry, never mind. But I know the facility exists. I just need the tie-in to be able to say, hey guys, give it a try. Here's the information. If you need more information, I can help, but give it a try. And if they did, and they found out all of a sudden satellites could use radiation reflection pressure instead of ion propulsion, would I hear about that? No, of course not. DARPA would just give some black project a grant for, $10 million to prove it out, and then $100 million to make it plausible. And then all of a sudden, NASA would discover this new fascinating means of propulsion. I still remember putting out the video on the difference between what I was saying was photonic propulsion and what the EM drive folks were saying. And I was just saying the EM drive is photonic propulsion. It's just extremely inefficient and doesn't really prove the point because the design's wrong. And I would get, emails from people on the YouTube channel about that. And to this day, one of the most popular videos on the Broward Astronomy YouTube channel is EM propulsion and photonic propulsion and how they compare. So I think there's people out there watching and listening in. I don't know you're out there, but there are indications.
Mm-hmm.
Okay, any more comments or questions before we stop recording? Hearing nothing.